Hi there and welcome back. Here we are ready to dive into the details of PL SQL. Alright, so this has been the last slide that we were looking at. The promise of the ability to write functions using a new language that is evaluated by the database system itself, by the database kernel close to the data. And that language would be PL SQL, or the PostgreSQL variant of that. So right. So the body of these functions, well, I've indicated the body as a block here, and for a good reason, because PL SQL is a block-oriented programming language. Blocks define the visibility of variable scopes. Blocks are used to control flow decisions. So all of that should be very familiar to you if you've ever programmed in any other procedural or imperative statement-based programming language. Let's look at blocks. Okay, so PL SQL code is indeed organized into blocks, and these blocks may be nested to express control flow and also to express variable visibility. So blocks define variable scopes. The syntactic elements of a block would be exactly these. So we would begin and end such a block with the begin and end keywords. Between these keywords, you would find a sequence of statements that would be processed from top to bottom, unless there is some iterating or conditional control flow inside these blocks. Okay, optionally, we might declare variables that are introduced just for this block and all the nested blocks that might be defined here in this particular space. All right, so variable visibility follows block structure, and that is probably exactly what you were expecting, right? So declare variables are in scope in this block, of course, in all the sub-blocks. Now, what happens if a sub-block declares a variable of the same name as any outer block? Probably also what you would expect. The local name takes priority and shadows all the outer names. Okay, so that would be the classical, probably the expected behavior that local shadows global, right? Well, PL SQL comes with a rather nifty possibility to introduce block labels. The syntax for these is a bit peculiar, so use these double angle brackets here, then assign a user-defined name, a user-defined label to this particular block. From then on, this block will be labeled by your label. And optionally, all variables that have been declared for this particular block, so let's assume that there's variable v declared in a particular block, could now also be accessed using this dot notation. The label, the name of the block, and then just the variable name v here. This makes it really easy to be very precise and explain to PL SQL which particular variant of variable v you would like to access and refer to if there are multiple variables v in scope. Right, so even if a local name shadows an outer name, using the label of the outer block will allow you to still refer to the block to the variable of the outer block. All right. There's even the convention that inside a function f, the top level block has an implicit label that is named just like the function. So all the variables, all the arguments that the function receives are treated like variables inside the body of the function, and they may be referred to with this f prefix using dot notation. Okay, so that makes it easy to always make sure that you refer to the arguments of the function f when there is a variable in scope that would be called just like one of the arguments. Okay, it's also helpful to refer to function arguments or variables inside blocks if you are processing embedded queries which uses column names, for example, that read just like the defined variables. This will help you. This labeled notation, this dotted notation here will help you to separate column names inside queries from variable and argument names inside your UDFs. Okay, so the block scoping, the block nesting, and the variable visibility is also being sketched here on this particular slide. So indeed, we are defining such a function f here with one parameter x1, right? And we are indeed using the PL/PG SQL, the PL SQL variant of PostgreSQL to define our function. Okay, so the function body itself is found between these double dollar signs. So everything between these double dollar signs makes up the body of this particular function. And there is no surprise, the body, of course, uses a block to organize the statements inside the body. Okay, so that would be the top level block here that we are defining. Optionally, we could label that particular block, and we do that indeed here using label O for outer. All right, so that would be the outer block of this particular function. Right. What other labels are in scope currently? Well, the implicitly defined f label. So all the arguments of the function, in this case it's only x1, could refer to everywhere in each block, regardless of the depth of nesting. They could be accessed everywhere using the name, the explicit name f.x1. So this will always be visible even if you are inside a block that defines its own variable x1. f.x1 will always refer to this particular argument, and it will also help to differentiate between column names inside queries that may be called x1 and the argument of this particular function. No confusion can happen there. All right, so let's assume that in this outer block we introduce a variable v here together with its type. Okay. What you will then be able, of course, is inside this block, which is this scope. Inside this block, of course, you will be able to refer to variable v here. You could also be very explicit and refer to o.v here. Okay. Inner blocks may be declared inside that outer block, and again we have explicitly labeled this inner block, which is of course optional, but since we redeclare a variable v here, okay, the labels allow us to be very specific inside this scope, where the variable v of the outer block would be shadowed by the new inner declaration. Inside this inner block, we can still refer to the outer variable by using these explicit labels. So that would be all the names that are in scope in this inner nested block. All right, so well, you will find that using these labels, block labels, is indeed the exception rather than the rule. But I think it's a quite sophisticated and very, very practical scheme to avoid confusion between variables in different scopes, and in particular variables and column names inside queries that may occur in the body of our functions. All right, so I brought a sample SQL file with me as always, and of course this will contain lots of UDFs, of PL SQL UDFs that are defined in there. So let's switch over there and have a look. What we will find here first is our old friend, the playground table T, that we've used in the very early chapters of this course. So welcome back, table T. We will be using you in the upcoming tiny PL SQL example. So let's define that and let's fill it with all the rows, the 5 rows that we know and love so much for many videos now. Okay, so here it is, back again, table T. Okay, so here comes our first SQL UDF, right? Let's have a closer look at what this thing does. But first, let me say that you will very often see these raise notice statements inside these functions. We haven't talked about the raise statement, and there will be a particular discussion about this raise statement in an upcoming video. But for now, let's simply assume that raise notice can be used to work like printf, to print log information or debug information to the pSQL terminal. All right, so what we are doing here is write this particular string, where this percent sign is included in the string, the result, the value of this expression will be placed in the output. So that would be a rather usual format string, as you've probably seen in many programming languages already. So raise notice would be our replacement for printf in the upcoming functions, until we explore the details of raising exceptions further in upcoming videos. Okay, so what are we defining here? It's function f. It's function f, and it's indeed defined in language PL/SQL as described on the slides. Since we are creating a persistent object inside the database with this create function DML statement, we have to make sure that such a persistent f function with the same parameter types is not already existent in this particular database. So what you will see is that we will always create these functions after we have dropped earlier versions that might be present in the database. This is a consequence of the persistent storage of functions. You will sometimes see that people write create or replace function f. And that would just do the same. So the function would be replaced if it's already present, or it would be created if function f has never existed before. All right, so just to mimic our behavior when we created persistent tables, I prefer the drop create pair of DML statements here, but you may use whatever you fancy. All right, so inside the body of this function f, which indeed receives a string parameter and then returns a new string again. All right, so it's a text transformer in a sense. So inside the body, we see these statements. Well, we start the body with this printf statement just to output the argument that we've just received. X here indeed refers to this argument x here. Since there is an implicit label that is named just like the function, at this particular point we could also write f.x, which anywhere in this particular body would refer to this function argument x. Okay, right. And it's very useful to have this scoped naming, this dotted notation for naming, because we are introducing a new variable x here that is also of type text. So to differentiate between the argument and this block local variable, we can use the dotted notation. All right, so inside that block, we assign a value to that variable. All right. And then inside that block also print the value of that variable, and then prove with the next print statement that we can still access the argument x that has been declared when we entered the function argument. All right. And indeed, we can also use the scope notation to alter the value of f.x, of the outer of the global f.x. All right. And once we leave this particular block and return x again here, well, this x and f.x are indeed the same variable. We could write fx here. And well, indeed, the old value of x has been overwritten. With the old value has been appended to this string overwritten, just to make sure that that we can see that the value of the received argument has indeed been modified. Okay, so well, if we execute this particular function, well, we would just invoke it. The invocation of function is for UDFs is no different than the invocation of built-in functions. We would just use parenthesized notation. F would be called with a single argument of type text here. So let's see what happens. Okay, so what we receive is multiple things. We of course we receive the return value of the function f, and you see that we have passed outer as the argument, and we receive overwritten outer as the result, just as expected. Okay, so that would be a value of type text, just what the signature of the definition of this function has promised. We read a text, we receive a text, and we return a text value. All right. As you can see, indeed, the raised notice have produced debugging output here on the pSQL terminal. And well, of course, in the outer block, in the top level block, X indeed has been our argument outer. Okay, nice. In the inner block, the name X now refers to the inner declaration of the variable X, which shadows the outer name, so that the value would be inner here. All right, but of course we can still refer to the top level X using f.x, and that's where that variable value instead is still outer. All right. What we can also demonstrate here is the optional naming of blocks. So I could have renamed this particular block and called it, for example, nested. Nested. All right. Cannot type. So that would now be a block named nested. Any variable declared in this block, for example, that X variable, could now be referred to by nested.x. Okay, right. And well, if we redefine this function and then invoke it again, we should see no difference in behavior here. All right. Okay, so that would be nested blocks and variable scopes in pSQL. Right. Back to the slides. So what we've seen is that with the opening of a block, with the declaration of a block, we can declare variables, like the variable of type text that we have just seen and declared. Right. So these variable declarations of a block are indeed optional. So we can use blocks purely to structure code, for example, to organize the control flow inside our functions. But of course, we can also use them to bring into scope variables that are block local. Right. And these are indeed typed variables. As you've seen, when we declared variable X, we assigned type text to this particular variable, and this is expressed by the declare statement in pSQL. So a new variable name is introduced, and well, the values of this particular variable will be of type tau. We can even initialize the value of that variable by specifying an expression of type tau, or an expression that can be casted to type tau. So v would be introduced, and it would immediately be assigned the value of expression e here. All right, if e is omitted, if this assignment is omitted, then v will have a value, the initial value of null of type tau. All right. We can make sure that such a variable will not receive a null value during the lifetime of its existence by adding this optional modifier not null here. All right, so any assignment of a null value to a variable in the flow of our program will yield a runtime error. Okay, so that can be used for debugging purposes, or also to shield yourself from unexpected null assignments to variables that may lead to problems later on. We may even declare variables as being constant. So what we indeed would declare would be constant here. This is of course only useful if you indeed pair this with this particular assignment. Right, so a constant v can be introduced. It can get an initial value of e, and will then be protected from any changes later on. Okay, so named constants can be introduced, can really help in making complex code better readable. Okay, there is one particular way of specifying the type of such a variable, and that would be using this particular construct here, which would refer to the type, of another variable named C, or of a column of a table named C. Okay, so we may refer to the type of a different name, of a different variable name, or a different column name, and use this construct in place of tau to declare our variable v here with exactly that type, the type of a different variable, the type of a particular function argument, or the type of a particularly named column here. Okay, so we can make sure that the type of variable matches the declared type of a column name, for example, because we expect that variable to receive values that have been stored in column C. We can make sure that the type of V and the type of C of that column coincide, so that assignment will be possible. Okay. Right, so let's have a closer look. Let's have a closer look at how this could look like in a real SQL UDF, PL SQL UDF. Okay, so what I'm using here is the possibility to declare polymorphic functions. All right, as you can see, I'm creating a function poly here, which will receive one argument x of any element. So any element. I think you might recall this from our discussion of polymorphic SQL UDFs, where any element would stand for any scalar type whatsoever. Okay, multiple mentions of any element, like here in the return type again, would refer to the same type. So this is indeed a polymorphic function that can receive a value of any scalar type and will then return a value of that same scalar type. All right, nice. To make sure that inside the body of poly we can work with a variable that has the same type as our argument x here, we use this peculiar x% type denotation of the type. So we declare name y here with the same type as our function argument x. So whatever x will be, it might be an int, it might be a float, it might be a numeric, it might be a boolean. The same type will be used to declare variable y. So it makes sense then inside the body to have assignment like this. So probably this will only make sense if the type of x will be numeric, but or any numeric type, int, float, or numeric actually. But because this operator, the multiplication operator, is polymorphic too, this expression indeed makes sense for more than a single type. It may make sense for all of these types, for example. And this declaration makes sure that y will be of the same type and can receive the result of this computation. And well, we then return it, which will be compatible with the return type, because y will have the same type as x, and that's exactly what is expected of this polymorphic poly function. Okay, so let's declare this. All right, and then invoke this once with a value of type integer here, indeed. And so y will be of type integer. This will be a multiplication that multiplies two integers. So we will return an integer. So let's see. Indeed, 2 times 21 is 42, the integer 42, right? So this is a floating point value, so any element will now be instantiated by float. Y will have the type float. This will be a multiplication of an integer with a float. The multiplication operation in PostgreSQL can do that, and we will return a float. All of this should fit together, and indeed what we receive is 4.2 here, so the float value. Indeed, poly is a polymorphic function. Indeed, its signature is somewhat too polymorphic because it accepts any scalar type here. So if we pass a boolean, for example, then y will have the type of Boolean, and this will be the multiplication between an integer and a Boolean. This will lead to a runtime error, and indeed this is what we will experience when we perform this function call. Alright, so this is the source of the problem. Indeed, there is no operator that can multiply an integer and a Boolean, and just like a SQL query that would have a problem there, just like that, this PL SQL UDF will struggle and then end with a runtime error. Okay. One more thing. Well, there's particular types inside SQL, and as I told you, the type system of SQL and the type system of PL SQL are actually coinciding. Actually, these are the very same thing. So we could have function arguments and also PL SQL variables of row types. Okay, and this is where this %sign type syntax really comes in handy. So let's assume that there is indeed a table T, right? And it has this particular row type. So table T has been declared with n columns named C1 to Cn. And well, these are the column types. The tau1 to tau n are the column types of table T. Recall that with the creation of table T, there will also be declared a row type of the same name. So I'm talking about this type here. This is type T, the row type that has n fields named C1 to Cn with field types tau1 to tau n. This is what is behind this type name, the row type name, capital T. Okay, and I can use that in the declaration of function arguments, for example. So this is indeed the row type. So inside the function, this variable, this argument T indeed has this particular row type. Okay, and since this function will be used to access the ith field, the field number I inside our row T here, well, we declare a local variable x that will indeed have exactly the have the type of the field numbered I, of field Ci. Okay, so I'm referring to particular table and column name here, right? And refer to its type, and that type, exactly that type, will be used to declare variable x. So now it's clear that variable x can receive values that have been stored in field Ci of table T. All right. And I will do that indeed by just using simple dot notation, the dot notation that we would also see being used in regular SQL queries. Okay, so this is a row type, so behind table T will, this is a row value, so behind this variable T, we will find a record that indeed has a field named Ci. I'm accessing that field. It will have type tau I. This is exactly type tau I here, and I can assign it to x and then return from the function. Indeed, the return type of the function has been declared using the same notation here. All right, so the return type will be the type declared for column Cy. Right, so this is a demonstration of how we can peek into the declared row types declared on the SQL side of things and then reuse them very easily on the PL SQL side. Okay, I've also brought a practical example with me just to demonstrate that. This is the function that will get the B field of row of type T here. Okay, so of course type T coincides with our table T. So let's look at T again. So this is type table T, and its row type will have 4 fields A, B, C, D. D will, I'm sorry, we're looking at B. B will be a field of type text here. Okay, right. So we are receiving such a row. We are receiving one row of our T table, right? And will access the B field. We know that the B field is of type text. This is exactly what we are referring to using this syntax. The type of the B field inside row type T, and this is just text. This is as good as writing text. Well, if the T table would be redefined later and column B would receive a different type here, well, this UDF would automatically adapt and would also always be it would also always be possible for this particular function to extract the B values from the rows of table T. Okay, so let's demonstrate that. Let's declare that function. And when we declare that function, notice that that PostgreSQL indeed tells us that that at this particular point of declaration of the function, that the type of the B field is indeed text. So it's as good as declaring variable x and the return type of the particular function as x. Okay, so everything should fit together. We should be able to evaluate this particular sample query here, where we indeed iterate over the rows of table T. So row variable T will be one row of our T table again. Well, with one such row, we will invoke the getB function. Okay, so as you can see, we can indeed invoke these functions in the select clause, in the where clause, in the having clause, everywhere where an expression of type text would be okay. We can invoke this particular PL/SQL defined UDF. Right, so we would access the B field of our row T and then, well, just compare it with X. And if this is satisfied, then just dump the entire row here. So let's see whether this works. And indeed, it does. So we see all the rows in table T in which the B field indeed is of value X. Well, which of course could be expressed like this, but who knows? All kinds of complex computation could have been performed inside the body of getB here. All right, so a communication between the type system of PL/SQL and the types defined on the SQL side of things is being expressed using this %type notation. All right, so much for the definition of blocks, of scopes, of variable declarations that respect such scopes of the visibility and the labels that we can use to have a very fine-grained access to the variables in different scopes. All right, I think that should set the scene for a discussion of all the different types of expressions that we can use inside PL/SQL. But this is a topic for the upcoming video. I hope to see you then. Bye-bye.